we will be discussing linear algebra and then calculus, probability. We will follow this order, and I'll be recapping the most important things for your exam point of view, and then we will also solve problems related to them. Okay, so let's start with linear algebra first. So when I think of linear algebra, the first thing that comes into my mind is multiplication. How can I multiply two matrices? How many multiplications, how many additions are needed? So let's recall that. If A is a M cross N matrix, B is a N cross P matrix. If you multiply, you get a new matrix, that is AB, which is M cross P. In obtaining this matrix AB, the total multiplications needed is M into N into P, and the total additions needed is M into N minus 1 into P. So this is one of the important thing. This was asked in the previous gate. You should also know the different types of matrices. So you can start with what is idempotent matrix. Idempotent matrix has a property that A square will be A. Students, if A square is A, can you tell us what is A cube then? Let's ask the students, what is A cube? And all the students are saying A cube is also A, excellent. A cube is A power 4 will also be A, and so on. What is involutory matrix? A matrix which satisfies A square equal to I. So let's ask the students, what will be A cube then? What will be A power 4, and then so on. Let's see what are your replies. What is A cube? When A square is I, A cube will be A, and A power 4 will be I, and then so on. So now what is nilpotent matrix? Nilpotent, where n square, not n square, you can write n power k actually, n power k will be null matrix for some positive integer, maybe like let's say k equal to 2 or k equal to 3, and then so on. The moment n power k becomes 0, then the higher powers like n power k plus 1 will also be 0, n power k plus 2 will also be 0, all higher powers would become 0. So let me cover all such things at one place. What about orthogonal matrix? Do you people remember the condition for the orthogonal matrix? A into A transpose equal to A transpose into A equal to I. Or some say this is this, or you can also say like this, where A transpose is nothing but A inverse. So this is the orthogonal matrix. There are two really interesting properties of orthogonal matrix. Do you remember it? Like the rows or the columns of orthogonal matrix are orthogonal to each other. When you find the norm or the length, we say, or the Euclidean norm, it is always 1. These points have been asked in your previous gate examination, so you are supposed to know them. In the exam, instantly you have to answer it. The columns are rows of an orthogonal matrix. are perpendicular to each other. This is the first point, okay? The next point is, this is called the length. The length, or this word Euclidean norm can be asked in your exam, don't confuse. Euclidean norm of columns or rows is equal to 1. Okay, this is about orthogonal matrix. So if I ask you, can you create one orthogonal matrix? Come on, can you create it? Does anyone remember the most important 2 cross 2 orthogonal matrix? Do you people remember it? I remember one of the orthogonal matrix, which is very important, which I teach in the class. A equal to cos theta minus sin theta, cos theta. So this is an orthogonal matrix. You can substitute any value of theta, it will be orthogonal. So this is about the orthogonal matrix. Next, symmetric matrix. I will share this notes as a PDF file to you all. You do not worry. If you are writing a running notes, that's even good, because your handwriting, your handwritten notes is even more useful for you. So what's the condition for a symmetric matrix? The condition is that A transpose has to be equal to A, or simply Aij should be equal to Aji. This is the condition for a symmetric matrix. So what's a skew symmetric matrix? Where A transpose equal to minus A, or you can say Aij equal to minus Aji. So this is a skew symmetric matrix. There is an interesting property about skew symmetric matrix. The principal diagonal elements of a skew symmetric matrix are always 0. So you have to remember that. Are always 0. And if a odd skew symmetric matrix is given, skew symmetric matrices of odd order, the determinant is 0. So this can be asked, and you can save a lot of time in this. The determinant of skew symmetric matrix of odd order is always 0. The determinant of skew symmetric matrix of odd order is always 0. So this can be like asked. So let's proceed. Let's learn few more things. So there was one interesting case, So it's like, I'll discuss this because this was also asked in your examination. Suppose if I give you a matrix like this, 1, 2, 3, 4. Students, tell what kind of matrix is this? Is it symmetric or skew symmetric? Satvik says neither, Akshay says neither, none. Ayush Gupta says none. Yes, this is neither symmetric nor skew symmetric. Neither neither symmetric. I missed symmetric. Okay, neither symmetric nor skew symmetric. neither symmetric nor skew symmetric. So, you people know who are listening to this lecture, you know what I am going to teach. So, when a neither symmetric nor skew symmetric matrix is given, it can always be expressed as sum of symmetric and skew symmetric matrices. So, A can be expressed like what? The symmetric part plus skew symmetric part. In the examination, in the past, there have been questions on, what is that symmetric part? What is that skew symmetric part? They have asked questions this way. So come on, try to recollect what is the symmetric part of A. The expression is, it is A plus A transpose by 2. What is the skew symmetric part of A? It is A minus A transpose by 2. Now, if you can find that, the symmetric part, whatever new matrix you get, it will definitely be symmetric in nature. When you find the skew symmetric part, it will definitely be a skew symmetric matrix. So that's how you can verify your answer. Sir, how do you say that? Okay, so come on, find A transpose as well. So where shall I write A transpose? So let me adjust it here. This is A. I need to write A transpose so that I can add them, subtract them properly. Come on, what is A transpose? This is a row, write like a column. This is a row, write like a column. Now what? A plus A transpose by 2. Add them. 1 plus 1 by 2 is 1. 2 plus 3 by 2 is 2.5. 3 plus 2 by 2 is 2.5. 4 plus 4 by 2 is 4, na? This is called the symmetric part, students. Similarly, find the skew symmetric part where I have to subtract and then divide by 2. So 1 minus 1 is 0. I am happy. Principal diagonal elements must be 0. So I am happy for that. 2 minus 3 by 2 is minus 0.5. 3 minus 2 by 2 is 0.5, and then 4 minus 4 is 0. I am very happy for this calculation. The principal diagonal elements are 0. So this is called the symmetric part of A. This is called the skew symmetric part of A. Now some students will ask, why did you put 2 here? Why did you put 2 here? The idea is, when you add the symmetric part with the skew symmetric part, you have to get back that matrix A. So come on, if you add 1 plus 0 is 1, matching. 2.5 plus minus 0.5 is 2, matching. 2.5 plus 0.5 is 3, matching. 4 plus 0 is 4, matching. If you don't put that 2, then adding this 2 will not generate the matrix A. These things have been asked in your previous examinations. You have to be alert. You have to know these things instantly. There you will not say, I will derive. So, it's like you will already analyze all this in the exam, instantly you will retrieve this. So, this is about symmetric, skew symmetric matrices. So, what next? What shall we discuss? I don't want to discuss the conjugate because for computer science and data science, you don't get questions on Hermitian matrix. So, what I would like to do is, I would like to quickly tell you what is a triangular matrix, diagonal matrix, identity matrix and so on. So, how does a triangular matrix look? Students, this discussion is very simple. As the class progresses, the discussion becomes more and more interesting. I will be taking up the problems. So, this is like a revision session. Each and every topic has to be recapped, and then I will also solve the problems. I need your cooperation. So, if you can sit till the end of the session, the entire subject would be revised, and in the process you will also be solving the problems. So, triangular matrix means, I think of upper triangular, which is like this: U11, U12, U13, U21, U. So, when I say upper triangular, is this 0? Is this element 0? Yes. This is U22 and this is U23. Is this 0 for upper triangular? Is it 0? Yes. This is U 3 3. In LU decomposition, we need U, which is the upper triangular matrix. So you should know how to identify that. It's easy to identify the upper triangular matrix. This is the principal diagonal. Below that, all the elements are 0. Come on, let's create a lower triangular matrix. I know these things are very simple, but simple things when implemented can solve the complex problems, okay? So I have to create a lower triangular matrix, okay? L11, 0, 0. L21, L22, 0. L31, L32, L33. So this is how a lower triangular matrix is going to look like. In LU decomposition, a matrix A is factored or decomposed into L into U, where you have to extract the elements of L, where you have to extract the elements of U. So that's a different story. So let's proceed. After this, let's discuss about the diagonal matrix. This diagonal matrix, upper triangular, lower triangular, will play a crucial role in finding the determinants, in finding the rank, in finding the eigenvalues, okay? So you have to have a good idea of this. How does the diagonal matrix look like? It has got elements like this: D11, 0, 0, 0, D22, 0, 0, 0, D33. This is a diagonal matrix. So let me also show you what's a scalar matrix. And by the way, what is a diagonal matrix? The principal diagonal elements, apart from the principal diagonal elements, the remaining elements are 0. So this is called the principal diagonal. Above the principal diagonal, below the principal diagonal, whatever elements you have, they are all 0. So scalar matrix, how does this look? It is similar to this, where in the place of D11, you have to write just D, 0, 0, 0, D, 0, 0, 0, D. All the principal diagonal elements are fixed and they are equal to each other. You cannot say 1, 2, 3. If you say 1, this is also 1, this is also 1. If you say k here, k, 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 and remaining all elements are 0. And please students, this identity matrix is going to be very helpful in your verification process. In the classroom, you would have already seen me solving the verification, like problems related to verification, where I take the identity matrix as reference. Okay, so this is a very important thing. How does I2, or some people write I2 cross 2, 1, 0, 0, 1. How does I3 look like? 1, 0, 0, 0, 1, 0, 0, 0, 1. This is how it is going to look like. These are very important patterns that one has to revise. Now, you know, I discuss about positive definite matrix. You should have an idea about positive definite matrix. Maybe today, I mean, towards the end, I'll try to discuss, but I'll just put a question mark here. So let's ask the students, what's a positive definite matrix? Towards the end, let's try to answer this, but this is also an important observation. Certain problems can be solved using the positive definite matrix with the knowledge of positive definite matrix. So what next? So we have done a quick recap of the basic matrices. This matrices can be asked in your examination in the 2025 paper. Next, do you know what's the next important topic? The next important topic is the determinants, students. The next important topic is determinants. So if I give you A, B, C, D, the determinant is calculated as AD minus BC. if I give you A, B, C, D, E, F, X, Y, Z, you should be skilled, okay? In a matter of 20-30 seconds, you just have to calculate a 3 cross 3 determinant. I don't teach any shortcut here. So you should be solving it in a matter of 20 to 30 seconds for a 3 cross 3. However, a 3 cross 3 determinant will not be asked if you look at the past data, but maybe in some process, like maybe in finding eigenvalues, or in some other case you might need this determinant. So how do you find it? This is A into, it's Ez minus Fy, and then minus B into dz minus Fx, and then plus C into dy minus Ex. This is how you find the determinant. Some values would be given. Can you find this in a matter of 20-30 seconds? You should train yourself to do that. Okay, so please remember. Ayush Gupta says, is Hermitier important? Not important, Ayush, because computer science, data science most of the time deal with real entries. So you don't need complex valued matrices. It's of no use for you, at least for gate level. So that's why I don't discuss for you. Can you people just calculate this in a matter of 20-30 seconds? You should do. By now you would have solved many problems. Now what I would like to revise is the row operations. Elementary row operations. These are really important. So this is the right time to once again tell you the importance of elementary row operations. Some of you might have forgot, but look at the heading. What are this called? Elementary row operations. This is one of the most important sections. It's like every problem we use this elementary row operations. Let's learn them properly and how do they impact our determinant calculation. So the first one is called the type 1. So I train students saying this is type 1, where we interchange rows I and j. So if you interchange rows I and j, then the determinant will change. For example, if A is a matrix like this, and you say R2 is interchanged with R3, so with this you get a new matrix called B, A, B, C, and then X, Y, Z, and then D, E, F. Do you people know the relation between the determinant of A and determinant of B? So the determinant of B is minus the determinant of A. You know, this question appeared in 2024 computer science paper, you know, this simple question. But they did not use the word interchange rows. They used the word swapping. So shall we check that question? I have just confirm it. 2024 computer science paper. I don't know the set. There were 2 sets now. Let's randomly check both of them. Now why am I saying this is, these things, simple things will appear in your examination. You can go through the paper. Maybe it was a 1 mark question. So let me check set 2. So do you, if you remember, you tell me in which set it was asked so that I can verify. Yeah, got it. 2 mark problem. Silly problem. What is this? Which of the following statements is R true? Is R means MSQ. A is a n cross n square matrix. B is a matrix obtained by swapping 2 rows. which one of the following statements these are true? The determinant of B is the negative of the determinant of A. True statement. If A is invertible, then B is also invertible. I need to verify. If A is symmetric, then B is also symmetric. If the trace of A is 0, then the trace of B is also 0. Let's solve this problem. It was asked in 2024. By now you would have already solved. This is for those people who did not try this problem. Yes, such simple questions have been asked in your examination. So you should be very alert and then solve this. This kind of questions should give you a lot of confidence, you know. Array, questions can be asked related to simple things. But I thought the question is MCQ, but it is MSQ. Okay. Swapping two rows means interchanging the two rows. So the determinant will change by a minus sign. Yes, this is true. Nothing wrong in this. If A is invertible, then B is also invertible. So now, how quickly can you tell that? So I can do this argument. If A then I can say the determinant of A is not 0. Invertible means non-singular, right? Non-singular means det A not 0. Now what is determinant of B, which is obtained by swapping, minus the determinant of A? When det A is not 0, minus of that is also not 0. When the determinant of B is non-zero, yes, B is invertible. This is a true statement. It's a true statement. If A is symmetric, then B is also symmetric. So how can you do that? Maybe create some simple matrix. 1, 2, 2, 3. Is this symmetric? Yes. What is A transpose? So I have to, first of all, A equal to A transpose. A is a symmetric matrix. We do not have any doubt. But how is B created? Let's interchange R1 and R2. So if you interchange, so first of all, before that, let me write A transpose is A. I do not have any doubt. This is a symmetric matrix. Now let's swap the rows. Let me create a new matrix. What's a new matrix? 2, 3, and then 1, 2. This written here and this written here. Is B transpose and B same? B transpose is not B. So this is not true. This is false. If trace of A is 0, then the trace of B is also 0. Is it? The trace of A is 0, it seems. Let's create one example. What is trace of A? 0. Let's interchange R1 and R2. You get B. What is B? This is going here and this is coming down. This is 1, 0, 0, 1. What is trace of B? So here, trace of A is 0, whereas trace of B here is 1 plus 1, which is 2. That is a false statement. False statement. So the answers are option A and B. Such simple questions were asked. Believe in your basics. If your basics are strong, you are unstoppable in the gate examination. Let's proceed. I'll just give you a minute. Observe these things. So I was discussing about the elementary row operations. This is called type 1, where interchanging rows I and j, the determinant will change by a negative sign. Let's discuss type 2. So what is type 2? So multiply rho I by alpha which is not 0. This is type 2. So imagine there is a matrix like this. Let's say you have multiplied R3 with alpha, then the new matrix is A, B, C, D, E, F, and then this is alpha X, alpha Y, alpha Z. How are the determinant of A and the determinant of B related? So try to recollect this. The determinant of B is alpha into determinant of A. Here you can do a mistake. The mistake is like this. So please don't do this mistake. So what's that mistake? The mistake is, if you have a matrix C which is obtained by alpha into A n cross n, where alpha is multiplied to each and every row, the determinant of C is alpha power n into determinant of this n cross n. These properties were asked in your examination many times. Students in that tense moment, all the time, like when I talk to the students, they have reported saying, sir, it was like alpha into A. I took the determinant as alpha into determinant of A. So the answer is alpha power n into determinant of A. The difference between them is here only a particular row is multiplied by alpha, but if you look at this, all the rows of A are multiplied by alpha. All the rows, or you can say each and every element of A is now multiplied by alpha. In that case, the determinant is alpha power n. This is type 2. Type 3, you will use type 3 definitely in 2025 examination. So you should have a crystal clear idea about type 3. So what is type 3? This type 3 is also useful for LU decomposition. LU decomposition is there for computer science and data science. It says, so my students know this statement. I asked them to repeat in the class. So what is that? Replace jth row by jth row by combination of itself and multiple of ith row. This is called type 3. Look at the heading, it's called elementary row operations. It's not called elementary column operations. So some students keep asking, sir, can I do column operations? When you are trying to find the determinant, yes, you can use elementary column operations also. But in our course, there is a section called system of linear equations where we don't do column operations. So every time we do row operations there. Row operations are valid and column operations are invalid. But when it comes to the determinant, you can use row operations or column operations, it doesn't matter. But to make a uniform approach, so what I always do is I just follow row operations only. So how is this written? Replace the jth row by combination of itself plus multiple of ith row. So it's written like this, Rj is replaced with Rj plus alpha times Ri. Please understand that when I say itself, it's like 1 into Rj. You cannot write 2 into Rj or any other scalar. No. Itself means Rj plus some multiple of ith row. So I'll give you one example. This is a section where the students can go wrong. In that tensed moment, in exam time, you might do a mistake here. So just create a matrix and then revise this. Again, take a matrix A, B, C, D, E, F, X, Y, Z. Create a matrix B. Let's say R3 is replaced with R3 plus alpha R2. Come on, how do you read this? Third row is replaced with itself plus a multiple of second row. So you get a new matrix that is B. What is B? The first two rows are unchanged, retain them. A, B, C, D, E, F. Come on, the third row, it's like X plus alpha D, Y plus alpha E, and then Z plus alpha F. This is how the new matrix is created. Now the beauty of this operation is the determinant is unchanged. The determinant of B is equal to determinant of A. See this? With type 1 the determinant value is changing, and that is like a negative value, negative sign you have to add. And here the determinant of B is alpha times determinant of A. And look at this, the type 3 operation do not change the determinant. This is one of the biggest operation, the most important operation, the most frequently used operation in our linear algebra course. I keep writing like this, the operations that do not change the determinant versus the operations that change the determinant. So let's revise that also. Operations that do not change red value versus the operations that change determinant value. So you people should know these points. Suppose you say R1 is replaced with R1 plus alpha R2, the determinant is unchanged. You say R2 replaced with R2 plus alpha R3, the determinant is unchanged. R3 replaced with R3 plus alpha R1, the determinant is unchanged. Instead of this, by mistake, if you do this, R1 replaced with alpha R1 plus R2, the determinant will change. And you use this keeping in the mind that the determinant is not changed, you get a wrong answer. R2 replaced with something like alpha R2 plus R3, the determinant will change. R3 replaced with some alpha R3 plus R2, the determinant will change. Now, I have observed this pattern in the GATE examination. There were crucial questions, like the matrix would be big, 4 cross 4, 5 cross 5, 6 cross 6. Please remember, you take this granted. In the GATE examination, if you get a 4 cross 4, 5 cross 5, 6 cross 6, patterns would be there. They don't randomly give you matrices. If they randomly give you some entries, it's difficult to solve. They always give you patterns. Please remember this. They always give you patterns. So it is with your practice, with your consistency, you will quickly decode the pattern, and in a matter of a minute, you have to solve it. So in such big problems, 2-mark problems, I found this operation was the crucial thing, where R1 is replaced with R1 plus R2 plus R3 plus so on Rn. This does not change the determinant. You can read it like this. R1 is replaced with itself plus combination of the other rows. So you can also do it like this. R1 replaced with R1 plus alpha 2 R2 plus alpha 3 R3 plus so on alpha n Rn. The determinant is unchanged. The particular row is replaced with itself plus the linear combination of the other. The beauty of this operation is it doesn't impact the determinant. In some of the most typical problems, especially this property was very useful, So I'll show you 2 such cases or 3 such cases, all such cases where the 2-mark problems in the GATE examination. So I hope you are very alert with these operations. Can you recollect this from our classes? I'll show you those. I'll put those questions in front of you. So observe them, and it's like we are anticipating such questions. We are expecting that questions in our examination. I'm trying to recall that question. I'll put such patterns here. This was one question, 2 1 1 1 1 2 1 1 1 1 2 1 1 1 1 2. The determinant of this was asked in the examination. Okay, first let me list out those cases and show you what is the pattern involved. There was one more question like this: 1 2 3 4 5. This is called the cyclic matrix, students. So you bring this last element here, and then this like this, continue in a cyclic way, you construct it. Bring this last element here, and then cyclic way you construct the entries. So this was not, the determinant was not asked. The eigenvalue, one of the real eigenvalue of this matrix was asked. Yes, these are asked in your GATE examination. What was asked? One of the eigenvalue was asked. Let me show you another problem which was related to the rank. So revision session means, yes, you have to tell you that these things were asked and you people should be alert. These things you have to recap. So what was asked? This pattern was asked. 1 1, no, not 1 1 1 minus 1 0 0 0, and then it's like 0 0 1 minus 1 0, and then 0 1 minus 1 0 0 minus 1 0 0 0 1, and then 0 0 0 1 minus 1. This pattern, all the 3 are the 2-mark problems which were asked in your GATE examination, and they have a pattern. Can you decode them? Let me decode this pattern. If I add all these elements, I get 5. If I add all this, I get 5. If I add all this, I get 5. If I add all this, I get 5. Now if I do that column wise, I get 5. You can check it. If you add them column wise, you get 5, 5, 5, 5. Come on, look at this. If you add all this, you get 15, 15, 15, 15, 15. And then here you get 15, 15, 15, 15, 15. So these patterns were given. You can observe these things. So it's like they create the matrix in a cyclic way. In all these problems, using R1 or replacing R1 with R1 plus R2 plus R3 will be a game changer, you know. In a minute you can solve such problems. What about this? If you add all these elements, you get 0, you know. If you add all this, you get 0, 0. Check it, 0, 0, 0. Do it column wise, you get zeros. These patterns were asked. I'll just list out what questions were asked in this. So in that particular GATE exam, the determinant of this matrix was asked. In this particular GATE exam, so they say there are 5 eigenvalues. and it has only one real eigenvalue, and what is that real eigenvalue was asked. And here the rank of the matrix was asked. In all these problems, the game changing step is R1 replaced with R1 plus R2 plus so on Rn. If you do that, the remaining things get simplified easily. So I was telling you about elementary row operations and the patterns that were given. Let's proceed. Now the properties of the determinant. I'll put all the properties at one place. So, do you know what is determinant of AB? It is determinant of A into determinant of B. Do you know what is determinant of ABC? It is determinant of A into determinant of B into determinant of C. What is determinant of A square? It is det A whole square. Or in the same way, what is determinant of, let's say, A power m? It is det A power m. So things can be simplified easily like this. Some students, they misunderstand and they assume that the determinant of A plus B is equal to det A plus det B. This is not true in all cases. You have to be extremely careful. Det of A plus B is not equal to det A plus det B. What else? The determinant of A transpose is always equal to determinant of A. If you are given a triangular matrix, upper triangular or a lower triangular or a diagonal matrix, so the determinant is the product of the principal diagonal elements. So let me write those things. Triangular and product of principal diagonal elements. So for example, we frequently use this 1, 0, 0, 1. What's the determinant of the identity matrix? The determinant of the identity matrix is 1. You take determinant of any identity matrix, it will be 1. Suppose you take 1, 2, 3, 0, 4, 5, 0, 0, 6. What kind of matrix is this? You highlight the principal diagonal. Below the principal diagonal, the elements are 0, so the determinant is very simple. It is 1 into 4 into 6, which is 24. So the determinant of a triangular and diagonal matrix is equal to the product of the principal diagonal elements. There are many such properties, so let me discuss them one by one. So the properties, like, suppose you have so what's happening here? There's a particular row which is completely 0, so the determinant is 0 students. So there's a, look at this case where you have identical rows. So whenever you have identical rows or identical columns, the determinant is 0. Observe this. What's your observation? So there is a third row, there's a third row which is just a scalar multiple of the first row. In that case, the determinant is 0. Now everyone will identify this. Come on, can you identify this? A, B, C, D, E, F, A plus D, B plus E, C plus F. So what's the observation here? The observation is that R3 was created in this way, R1 plus R2. Now when you have, this is actually called linear dependency. What is this called? Linear dependency. There is a topic called linearly dependent and independent vectors. So there also this idea is important. when you have got some linear dependency, this is a simple linear dependency like R1 plus R2, just adding it. In the exam, it can also have alpha 1 R1 plus alpha 2 R2, which is difficult to decode. But let's say if such a simple observation is given, there is a linear dependency, without any hesitation, the determinant is 0. And you know, such question was asked in the exam in a DA paper 2024 examination. I'll show you that. I hope you are all recollecting this information. So let's proceed. Let me also open the DA paper. Yeah, this was the question. 1 mark problem. Students, whatever properties we are discussing, you will get questions from those properties. So what's the question? Can you people recollect, or can you observe what's the relation between the rows? I can see that this is 4, 3, 6. This is will this work? 1 plus 3 is 4, 2 plus 1 is 3, 3 plus 3 is 6. So what's happening? R3 is simply R1 plus R2. R3 is equal to, okay, R3 equal to what? R1 plus R2. So when you have such linear dependency, the determinant of matrix M is 0. But the question is not about the determinant of M, the question is about M square plus 12M. M is common. When M is common and it is written, then this is M plus 12I, not 12, it is 12I. And now this resembles like determinant of A into determinant of B, which can be written as determinant of M into determinant of M plus 12I. So obviously, so this determinant of M is 0, 0 into this value will be anyway 0, the final answer is 0. Such simple question was asked. It is simple when you know these properties. You know how people can make this complicated? People can complicate this by saying first find M square and then find 12M and then add it, and then you get a new matrix, find the determinant of the new matrix. This is how the things can be complicated. You will get the answer, but things get complicated there. So, where did that question go? Yeah, we were discussing the properties. These are some of the properties. So let me add a few more. What is the determinant of A inverse? It is 1 by determinant of A. What is the determinant of adjoint A? So as far as I remember, it is determinant of A power n minus 1. I usually derive this. So far, questions on adjoint A was not asked. This is an untapped section. So these are the properties. Do you have any other properties? If you have any, please recollect them. I'll write it on the screen. Yes. So skew symmetric matrix of odd order, determinant is 0. Did we write that during the skew symmetric? Yes, we wrote. So it's already covered. Orthogonal matrix, determinant is either 1 or minus 1. This can be asked. So this should give you a rough idea about the properties of the determinant. So I hope everything is going well, students. Rohit says adjoint of adjoint A. Yes, Rohit, do you remember adjoint of adjoint A? You don't get such things because in the past never questions appeared on adjoint A, and then if you want adjoint of adjoint A, I think it is det A power n minus 2 into matrix A. Please comment the answer about what is adjoint of adjoint A. Akshay Ganesh says it is det A power n minus 1 whole square, but that is a determinant of adjoint A. So there are two things. One is the determinant of adjoint A. Yes, it is det A power n minus 1 whole square. And you can also find an expression for adjoint of adjoint A. So this is what I was asking. Can you recollect what did I give it in the class? As far as I remember it, it is determinant of A power n minus 2 into matrix A. Can you recollect that and post it? Akshay says the same thing, that A power n minus 2 into the matrix A. These things never asked in the examination so far. Sorry, into A. And one more thing, please remember, if a question is asked on A inverse, do you know the verification trick? The verification trick is A into A inverse is same as A inverse into A same as I. This simple verification trick can save you lot of time in the examination. A into A inverse equal to A inverse into A equal to I. This verification trick will save you a lot of time. So these are the properties of determinants, students. Now let me teach the rank. So everyone knows that the easiest way to find the rank is convert the given matrix into row echelon form. You can use any number of row operations and then convert that to row echelon form. So once you convert that to row echelon form, the number of non-zero rows will be the rank. There are few important points about rank. Convert the matrix into row echelon form, count the number of non-zero rows, that is your rank. The rank also denotes how many rows or how many columns are linearly independent. For example, if I give you a 5 cross 5 matrix and I say the rank is 3, it means there are 3 linearly independent rows. It means that there are 3 linearly independent columns. That's the meaning of rank. So few important points like the rank of A m cross n is always less than or equal to min of m comma n. The rank of A into A transpose is same as rank of A transpose into A, same as rank of A. So suppose if you are able to multiply A and A transpose and A transpose and A, so whatever is the rank of A, the same thing is the rank for A into A transpose. Was this asked? Yes, this was asked in your examination. So try to recollect this. This were not asked. The rank of A plus B is less than or equal to rank of A plus rank of B. This was not asked. Rank of AB less than or equal to min of rank of A comma rank of B. This was also not asked, and again I feel this too can be asked. So let me revise few more interesting points. Suppose the determinant of a n cross n matrix is not 0. So that means a non-singular matrix. So what's the rank of that? So in that situation, the rank of A is equal to its order. Suppose it's a n cross n matrix whose determinant is 0, then in that case the rank will be less than its order. These are really important. You must know instantly. The other way is also true. If A is a n cross n matrix with rank n, you can say the det will not be 0. If A is a n cross n matrix whose rank is less than n, you can 100% confirm that the determinant of that matrix is 0. So these are interesting properties. What does the rank denote? This is the most important point everyone should know. What does the rank denote? Rank of A gives the number of linearly independent rows or columns. It gives the number of independent rows or columns of the matrix A. This is important, very important for computer science and data science. This idea that okay, the rank of A tells how many rows are linearly independent, how many columns are linearly independent. So they'll give you vectors v1, v2 up to vn, and they'll ask you whether these vectors are linearly dependent or independent. So when you club them, v1, v2 up to vn, let's club them, let's find the determinant. If the determinant turns out to be 0, you can call those vectors to be linearly dependent vectors. This is the simplest approach, students. This is the simplest approach. v1, v2 up to vn, if this determinant is not 0, then they form linearly independent set of vectors. A very important observation. Now some students will ask, sir, suppose if they give you vectors and I club them and I don't get a square matrix, how do I decide that, sir? That is, yes, a genuine question which was not asked in our examinations. Most of the time vectors were given in such a way that when you club them, you get a square matrix, a 3 cross 3 matrix or a 4 cross 4 matrix. In the past, these kind of questions were asked. But you can ask questions like, sir, I clubbed, but I got a 3 cross 4 matrix, sir. I got a 4 cross 3 matrix, sir. Then how do you find the determinant, sir? If you ask, then what you can do is, you can create this equation alpha 1 v1 plus alpha 2 v2 plus so on plus alpha n vn equal to 0. This is called the homogeneous equation. In the system of linear equations, this one is called the homogeneous equation. If this homogeneous equation has got the trivial solution, then all the vectors are independent. So I'll write, if you have only, so trivial solution means what? Trivial solution. What does trivial solution refer to? Where alpha 1 equal to alpha 2, so on, alpha n equal to 0 is the only solution. You don't have any other solutions. In that case, the vectors are said to be independent. Now in the case you have non-trivial solution, non-trivial solution means infinitely many solutions are there for this homogeneous equation. Now in that situation, they are called linearly dependent. You don't need to go up to this level because in the gate, so far whatever they asked things where after clubbing those vectors, we got a square matrices. The determinant approach has helped us in solving that. Come on, students, are you recollecting all this? These things were taught to you in the class. So this completes a discussion on rank. Then comes the system of linear equations part. In the system of linear equations, you can categorize like this. Non-homogeneous system, which is in the form of Ax equal to b. It has got three possibilities. So let's know what are they. The first one is the case of no solution. So when does this happen? This happens when rank of AB not equal to rank of A. Unique solution. When does this happen? When rank of AB equal to rank of A equal to number of variables. So you get unique solution whenever rank of AB is equal to rank of A equal to number of variables. The last case, which is infinitely many solutions, let's write that. So when does this happen? When rank of AB equal to rank of A. Rank of AB is equal to rank of A. But the two quantities are like this is less than n, where n stands for the number of variables. So you get infinitely many solutions in this case. Already this was given in the notes. A quick recap before your examination will boost you in problem solving. So the next one would be homogeneous part. Nishant says this is regarding Gaussian elimination. Yes, this is regarding the Gaussian elimination. This is related to system of linear equations. So the next case is like this. The homogeneous part. Homogeneous system. How does this look? This looks like Ax equal to 0. There are two possibilities. Let's analyze them. The first possibility is trivial solution. So where you have the rank of A equal to the number of variables. So I indicate the number of variables with n. Sometimes what happens is, in some special situations, the coefficient matrix given to you can be a square matrix. Usually it need not be a square matrix, but maybe in the examination they might give you a square matrix. Then the determinant approach will be very useful, you know. The determinant of A in that case is not 0. The moment that A is not 0, you can say that the corresponding homogeneous system has only trivial solution. And what's the meaning of trivial solution? All the variables x1 equal to x2 up to xn equal to, they are all 0, and this is the only solution. There are no other solutions, only one solution. And case 2 comes under non-trivial solution. Non-trivial solution. So what's the meaning of non-trivial solution? Or when do you get a non-trivial solution? Non-trivial solution means infinitely many solutions, and when do you get that is when rank of A is, so obviously what you said here is equal to n, here you have to say less than n. In terms of determinant, if you have to say, then the determinant of A has to be 0 here. But this is a special case, students. Whenever n is n cross n, then only you can use. If it's a rectangular matrix, the only thing that can save us is rank approach. So this is about homogeneous system. There are few more interesting points about these things. I'll highlight them. Homogeneous systems are always consistent, you know. In the place of x you put 0, A into 0 will give you 0. So they are always consistent. Non-homogeneous systems need not be consistent. For example, you try to put whether 0 solution is a solution or not. A into 0 is 0. How is 0 equal to B? It's not equal, right? So there might be a chance of no solution in the case of non-homogeneous, but whereas in the case of homogeneous system, it is always consistent. Now this is the most important point. If questions are asked on this, then the students might get confused. Imagine there are infinitely many solutions. Let's say you got a case like this, non-trivial solutions, infinitely many solutions. In those infinitely many solutions, how many are linearly independent solutions? I want to know how many of them are linearly independent. So look at the statement. The number of linearly independent solutions of the homogeneous system Ax equal to 0 is given by what? Can you people reply? I'll read your comments. The number of linearly independent solutions of the homogeneous system Ax equal to 0 is given by what formula? Abhiram says it is n minus r. Abhiram, can you also tell us what is n, what is r? It is number of variables minus rank of A. Yes, correct. It is n minus rank of A. It is given by the number of linearly independent solutions of the homogeneous system Ax equal to 0 is given by n minus rank of A. Students, I want to once again highlight. So now how do you say the system is consistent? How do you say the system is consistent? Please understand this. Whenever, this is what people teach you, whenever rank of AB is equal to rank of A, we say it is consistent. There is another equivalent thing that you can check. Both are actually equivalent conditions. So when B is linear, B is expressed as when B is expressed as linear combination of columns of A. So whenever they say that, look, there is a system called Ax equal to B, where A is like this, A1, A2 up to An, and they also give you a further information that B is like this, summation I from 1 to n, let's say some alpha I into Ai, some linear combination. You take the linear combination and you are getting B. The system is always consistent, you know. So implies system is always consistent. I have already explained problems on this. The theory part I have explained, you can recollect it. This is the right time to revise this most important point. And this particular point was asked in one of the most beautiful problems of linear algebra, which is already discussed to you in the class. So I just wanted to revise this point. Whenever B is expressed as linear combination of columns of A, in that case the system is consistent. Any of these conditions are true, the system is consistent. Both are equivalent actually. Are you recollecting this? There was one typical problem, you know, in the data science paper. It was very beautifully created. I want to solve that problem. Most of you got confused while solving that. Let's discuss that. Yeah, this is a problem. Two-mark problem, theoretical problem. Okay. Students, this was asked in the data science for 2 marks. One of the typical problems that was asked, you need good basics to answer them. Let's read it. Which of the following statements are true? MSQ. So where R denotes a set of real numbers. What's the first option? There exists M belonging to R power 3 cross 3, which means basically R is a 3 cross 3 real matrix, and P belongs to R power 3, Q belongs to R power 3 such that Mx equal to P has unique solution and Mx equal to Q has infinite solutions. Like that, various options are given. You have to identify which is true and which is false. Let's analyze them. Option A, I want to analyze. What is M? It's a 3 cross 3 matrix. What is P? It's a 3 cross 1 vector. What is Q? It's also a 3 cross 1 vector. They gave systems like Mx equal to P and also Mx equal to Q. So now just a rough calculation. When you say Mx equal to P, so what is M? It's a 3 cross 3 matrix. What is X? I don't know. So I have to find the order. So some order, when I multiply, the result is a 3 cross 1 vector P. So now what should be the order of X means? It should be like 3 cross 1. A 3 cross 3 matrix multiplied with 3 cross 1 will give you 3 cross 1 vector. So why am I asking this is, basically X has 3 variables. Extracting number of variables, students are doing the mistake. Don't do that mistake. You just compare like this. Mx equal to P means what should be the order of X, you have to guess. It's a 3 cross 1 which indicates there are 3 variables. Similarly, Mx equal to Q, so the same X is used there. What are they asking? There exists M, P, Q. So they are saying you can create a matrix M, a vector P, vector Q such that Mx equal to P has unique solution and Mx equal to Q has infinite solutions. So let's write like this: if M into X equal to P has unique solution, then what can you say? We can say that rank of MP has to be equal to rank of the coefficient matrix equal to the number of variables. How many variables are involved? Just now we concluded the order. It is a 3 cross 1 vector which has 3 variables. So the rank of MP has to be equal to rank of M and it has to be equal to 3. So keep this in your mind. What else they say? Yeah, where are we? First option, Mx equal to Q has infinite solutions. So now when you say that it has unique solution, for sure rank of MP has to be equal to rank of M and it should be equal to the number of variables. So that's clear. Mx equal to Q should have infinite solutions. So for Mx equal to Q to have infinite solutions, so we need rank of MQ equal to rank of M less than 3, because for infinite number of solutions there is a condition that rank of AB has to be equal to rank of A, but it has to be less than number of variables. Here we are saying the rank of M must be less than 3, and here already we said the rank of M is 3. So this cannot simultaneously happen. Our first option is false. Option A is false. So likewise, you have to now comment on the other options. Excellent problem, okay? Brilliantly created. It will take a lot of time for you to crack this. This is about what? This is about option A. Let's analyze option B. What are they saying in option B? There exists M, which is a 3 cross 3 matrix. Okay. P is a 3 cross 1 vector, Q is also a 3 cross 1 vector, and then Mx equal to P has no solutions and Mx equal to Q has infinite solutions. So the moment when you multiply Mx with P, you have to get the order of X. X is a 3 cross 1 vector, it will have 3 variables. That number of variables is very, very important. So again, the same discussion, right, like this: if Mx equal to P has no solution, then so when will Mx equal to P has no solution? Maybe like this: when rank of MP not equal to rank of M. This is when it can have no solution. So rank of MP is not rank of M. So when will this happen? And also in the next case you want infinite solutions. Students, I want to know what would be the order of MP. Order of MP. M is basically a 3 cross 3 matrix, okay, which has 3 rows and 3 columns, good. And what is P? It is a 3 cross 1 vector, so it's like this. So how many rows are there? 3 rows are there. And how many columns are there? 4 columns are there. So what is rank of, basically what is the order of MP means 3 cross 4. For a 3 cross 4, the rank is always less than or equal to 3. So now what I want to say is, let me just assume that, okay, let the rank of MP be 3. Can it be 3? Yes. Can you create such matrix M vector P means yes. And I want the rank not equal to M. So can you create M like this? Yes, we can create. Such M and P can be selected. So with this, let's read the next part. What does the next part tell? Mx equal to P has no solution. Yes, for that I have created MP such that the rank is 3 and the rank of M is 2. And then Mx equal to Q has infinite solutions. So for Mx equal to Q to have infinite solutions, Mx equal to Q to have infinite solutions, we want rank of MQ equal to rank of M but less than 3. This is what is a requirement. So can such M, P, Q exist? Let's see. We already said rank of MQ must be 3. So you can create M such that the rank of MQ is equal to rank of M equal to 2. Because already the rank of M, the first part was taken as 2. So such rank M equal to 2 can be created, and Q can also be chosen such that the rank of MQ is 2. This has no issue. Such M, P, Q can exist. It is a true statement. I really enjoyed reading this and solving this. This needs a great understanding of the subject. Great in the sense all the basics, your basics must be good to crack this problem. So this is about option B, students. Likewise, now we need to analyze the other two. This question you can get from the GATE paper, DA paper. Hope this is visible. So students, I hope the question is clear now. Sometimes the white background be little blur. So what next? We are left with 2 more options, C and D. So far we said option B is true, option A is false. So now let's verify option C. Option C. There exists M, which is a 2 cross 3 matrix, okay, 2 cross 3. P is a 2 cross 1 vector, okay. Q is a 2 cross 1 vector, okay, such that Mx equal to P has unique solution, fine. So they talk about the system Mx equal to P and Mx equal to Q. So when a 2 cross 3 is multiplied with something and the end result is 2 cross 1, then what should be the order of x? This is where the students are doing the mistake. They are unable to get the order of x. Can you people comment about the order of x? I want to listen from you people. Ayush Gupta says 3 by 1. Bhanu Prakash 3 by 1. Sai Harshit says 3 by 1. Yes, you are right. It has to be 3 by 1. So what is x basically? X is a 3 cross 1 vector. How many variables are involved? 3 variables are involved. What you want? Unique solution you want. So for unique solution, first of all, before you find the unique solution, can you people look at what is rank of a 2 cross 3 matrix? Rank of a 2 cross 3 matrix is always less than or equal to min of 2 comma 3, which is 2. The rank of this matrix can never be 3. So now I can tell that the rank of M can never be equal to the number of variables. It can never be equal to number of variables. Over. Finish. No, you cannot get a unique solution. He says mx equal to p has a unique solution, but I found that the rank of M is always less than or equal to 2, whereas the variables are 3. This 2 will never be equal, therefore unique solution is not possible. Option C is false. This is a MSQ. I have to analyze D patiently and then extract the answer. This needs a lot of conceptual basics. Chalo, the last option for verification. Option D. This time M is a 3 cross 2 matrix. Changed. It's a 3 cross 2, which implies the number of variables are 2. Earlier the number of variables were 3. That created a problem. What is Q? P. It's a 3 cross 1 vector. Q, 3 cross 1 vector. What is X? 2 cross 1 vector, which will have 2 variables involved in it. Mx equal to P has unique solution and Mx equal to Q has infinite solutions. Let's see, is that possible? If Mx equal to P has unique solution, then what? I can say rank of MP, that is the augmented matrix, has to be equal to rank of M has to be equal to the number of variables, which is 2. Can this happen? What is M? It's a 3 cross 2 matrix. What is P? It's a 3 cross 1 vector, so you have to write one more column. So what is MP? It's a 3 cross 3 matrix. The augmented matrix is 3 cross 3. Can a 3 cross 3 matrix called MP can have rank 2? Yes, it can have rank 2. Can the rank M, which is a 3 cross 2, can a 3 cross 2 matrix have rank 2? Yes, it can have. So this is possible. With this, the answer is not completed. There is another part that you have to analyze for the option D. Yes, Mx equal to P can have a unique solution, and can Mx equal to Q have infinite solutions? Can Mx equal to Q, sorry, where are we? Here we are. We have already analyzed C, we are analyzing D. So Mx equal to P has unique solution, yes, and Mx equal to Q has no solution. Mx equal to Q. So let me check it. I need to analyze Mx equal to Q. Mx equal to Q. No solution. Let me check. Rank of MQ. So already I have taken rank of M as 2. No solution means rank of MQ should not be equal to rank of M. What is MQ, by the way? MQ is also a 3 cross 3 matrix, yaar. Is it 3 cross 3? Yes. Can a 3 cross 3 matrix have rank 3? Yes, it's possible. If you select M and Q properly, you can have a rank 3. And can you have the rank of M to be 2? Yes, because earlier also you have used 2. So the same matrix can be used. But with change in P, or if P is replaced with Q with some different elements, the rank of MQ can be made 3. And whenever rank of MQ is not equal to rank of M, it leads to infinite solutions. So such M, such P, such Q can exist with this combination. This is a true statement. So infinitely many solutions are possible. So with this, what's the answer? What did we say? We said option A is false. This is false. And then we said option B is true. And then we said C is false. And then now we are saying D is true. So this was a MSQ and a very good question. I hope you people have understood this. Satvik Sinha, is everything okay now? Satvik Sinha says that what you wrote here is a mistake. He says in option D, we wanted no solution. Yes, you are right, Satvik. It is by mistake I wrote. So thanks for that. Maybe I was reading option C. So with this combination, rank of MP equal to 3 and rank of M equal to 2, so you'll have no solution. So you are right, Satvik Sinha. No solution here. Such M, such Q, such P can exist where Mx equal to P has a unique solution, whereas Mx equal to Q can have no solution. Satvik, is it okay now? I've explained everything properly, but I wrote a wrong statement there. Let's proceed with the eigenvalues and eigenvectors concept. Most of the problems are solved with this verification trick, students. Most of the problems are solved with this verification trick. What kind of verification trick? If the scalar lambda and the vector x satisfy Ax equal to lambda x, that's called the eigenvalue and the eigenvector. Lambda is called the eigenvalue, x is called the eigenvector. Many problems were solved with this trick, you know. How do you find the eigenvalues? We equate the determinant of A minus lambda I to 0. You will get a polynomial, solve the roots. The roots are called the eigenvalues. And then you will substitute them into this homogeneous equation, that is A minus lambda I multiplied with x equal to 0. You will substitute those lambdas and you will solve. So when you solve, it's a homogeneous equation, you will know what are those eigenvectors. It's like for every eigenvalue, there will be infinitely many eigenvectors. Please understand that. If A is n cross n matrix, there are n eigenvalues and each eigenvalue generates infinitely many eigenvectors. And you know how to find those, but in the examination, the properties dominate. So if you can use the properties, you can get the answer quickly. So what are those properties? The properties are like the sum of the eigenvalues is equal to trace of matrix A. Product of eigenvalues equal to the determinant of A. So if one of the eigenvalue is 0, then the determinant is 0. Determinant of A is 0. So you can also say like this. If determinant is 0, then at least one eigenvalue is 0. If det A is 0, then at least one eigenvalue is 0. So I hope everyone is following. I am reading your chat. So if you have any doubts, you can ask me there. We will go for a break in some time. Once I finish this properties of eigenvalues and eigenvectors, we can go for a break. If det A is 0, then at least one eigenvalue is 0. If det A not equal to 0 and lambda is an eigenvalue of A, then 1 by lambda is eigenvalue of A inverse. What's the eigenvalue of adjoint A? What's the eigenvalue of adjoint A? I think it is det A by lambda. And there is a big list like this now. Let us write them. Lambda square is the eigenvalue of A square. Lambda cube is eigenvalue of A cube. So lambda power m is the eigenvalue of A power m. A and A transpose have the same eigenvalues. A and A transpose have same eigenvalues. Now look at this. The eigenvectors of A and A transpose need not be same. The eigenvectors of A square, A cube up to A power m, A inverse, adjoint A. So when you have these matrices, they have the same eigenvectors. The eigenvectors of these are same. Was this asked in the exam? Yes, this was asked as MSQ. There are many such properties. Let's learn them. Let's revise them quickly. Students, suppose if you have a matrix like this, A naught I plus A1A plus A2A square. Some polynomial in A, where A is a matrix, I is an identity matrix. If they give you a matrix like this, ask you what is the corresponding eigenvalue, then the eigenvalue of I is 1, the eigenvalue of A is lambda, the eigenvalue of A square is lambda square. So substitute them. It is A naught plus A1 lambda plus A2 lambda square. A2 lambda square. So A naught I plus A1A plus A2A square will have A naught plus A1 lambda plus A2 lambda square as their eigenvalues. Suppose if they create a function called f of A, students, if they create a function called f of A, then that fellow will have an eigenvalue which is like f of lambda. The idea is very simple. Replace A with lambda, and if you have an identity matrix, then replace that fellow with I. Replace the identity matrix I with 1. So see, I replaced I with 1, so this is A naught. Replace A with lambda, so lambda square. Same way, if they create some function of A, they ask you what's the eigenvalue of f of A, then it is f of lambda. Is this important? Very, very important. So let me show you a few more properties. In one of the examination they asked like this. If A plus root B is the word real matrix is important, the real matrix A, then A minus root B is another eigenvalue. A plus root b is one eigenvalue, then its conjugate surd, which is A minus root b. A plus root b and A minus root b are called conjugate surds. So they always occur in pairs like this. The same thing, A plus IB is an eigenvalue of this word. Real is very important, of a real matrix. It's true for real matrix only. Of a real matrix A, then this is then, okay, then the complex conjugate of A plus IB is A minus IB. A minus IB is another eigenvalue of A. These properties were already covered in the classes. Just a quick recap. The problems were asked on this in your previous gate examination. So what are the other properties? Skew symmetric matrices eigenvalues are always real. What did I say? Let me tell a right statement. Symmetric matrices. I don't remember what I said earlier. Did I say skew symmetric? So the right statement is symmetric matrices eigenvalues are always real. This was asked in many examinations as a theoretical point. The eigenvalues of symmetric matrix are always real. What about the skew symmetric matrix? Either 0 or purely imaginary. Purely imaginary. If you have an orthogonal matrix, if you take the absolute value of your eigenvalues, it is either, okay, absolute value is always 1. Okay, I was about to write plus or minus 1. How the absolute value would be negative? So the absolute value is 1 for an orthogonal matrix. And then for a nilpotent matrix, all the eigenvalues are 0 for nilpotent. All eigenvalues are 0. There are few more properties. Just go through them. I'll just give you a half minute. Hope you're all following this. And after the class, this notes will be shared with you. Sai Vinay says, if the matrix contains irrational numbers which are also real, then the first condition can be wrong, right? Are you talking about this? Sai Vinay? So what I wrote is, if you have a real matrix, both rational and irrational numbers come under real matrix, so it should be true even for irrational entries. Sai Vinay, you can check it by creating example. If that doesn't work, you can ask me again. You have raised a doubt that if it contains irrational numbers, what's the problem? If it contains irrational numbers also, it should be like that. If a plus root b is one of the eigenvalues, then a minus root b is another eigenvalue. Irrational numbers also come under real numbers, so the whatever I gave should work. If it is not working, then you have done the mistake. Bring that problem to my notice, I will help you. Next, we have some critical properties like, so what are the critical properties? For the symmetric matrix, the eigenvalues, so I will write like this. then A has R non-zero eigenvalues. R non-zero eigenvalues and n minus R eigenvalues are 0. It's a very, very important one. N minus R eigenvalues are 0. The eigenvectors corresponding to the distinct eigenvalues of a symmetric matrix are always orthogonal and their dot product is 0. This is also very important. The eigenvectors corresponding to distinct eigenvalues of a symmetric matrix are orthogonal and the dot product of such eigenvectors and dot product of such orthogonal vectors is 0. These things have been asked in your past examination. So there are few more properties. Let's complete them. Cayley-Hamilton theorem. It says every square matrix satisfies its own characteristic equation. So suppose 3, 2, 1, 2 is matrix A. What's the characteristic equation? Write A minus lambda a matrix, which is 3 minus lambda, 2, 1, 2 minus lambda. Equate its determinant to 0. 3 minus lambda into 2 minus lambda minus 2 equal to 0. 6 minus 3 lambda minus 2 lambda plus lambda square minus 2 equal to 0. This is giving me lambda square minus 5 lambda plus 4 equal to 0. This is called the characteristic equation, students, in lambda. What Cayley-Hamilton theorem says is, in the place of lambda, put A, you get a new equation or new expression. Now that is also a true equation, it seems. That is A square minus 5A plus 4I will give you a null matrix, it seems. In the examination, there were some typical problems on Cayley-Hamilton theorem where you people have to correctly find the characteristic equation. If you can find the characteristic equation, you will get the answer. So let me put one question on the screen. Let's see whether you will give me a proper characteristic equation or not. So I have an example problem for you. I need its characteristic equation. This is already solved in the class, but just I want to make sure you people have the enough practice. What I want a characteristic equation for a problem. Okay, I am just searching for the numericals, students. Okay, come on. If these are the entries, one, 0, 0, 4, 0, 4 minus 2, 0, 1, 1. Can you give me the characteristic equation in lambda? I'll give you 2 minutes time. Can you give me the characteristic equation? Let's see how many of you will answer the characteristic equation. This is really important calculation, students. Chandra Harsha says a square minus 7a plus 6, that is wrong. Akshay Ganesh, can you please write your answer clearly? Dikshi Reddy says a cube minus 6a square plus 11a minus 6 equal to 0. Looks like this is right. Nitika says exactly the same answer. Please understand, if such a problem is given, you should be able to write that in a minute. Some of the students give the correct answer with less than 2 minutes. That's really good. That shows you are preparing well. Okay, she says fine. And I can see in the chat section students giving me the same answer. So means the majority are right. So let me try. A minus lambda I determinant has to be made 0. So 1 minus lambda 0, only the principal diagonal elements change. 0, 4 minus lambda minus 2, 0, 1, 1 minus lambda. This determinant has to be 0. You can expand using the first row because it has more zeros. So it's like 1 minus lambda into 4 minus lambda into 1 minus lambda plus 2 has to be 0. So you have to simplify in the usual way. 1 minus lambda into 4 minus 4 lambda minus lambda plus lambda square and then plus 2. Your calculations must be so quick. This is 1 minus lambda and this is lambda square minus 5 lambda, is it plus 6 equal to 0, and then you have to further multiply this. This gives you lambda square minus 5 lambda plus 6, and then minus lambda is multiplied, which gives you minus lambda cube plus 5 lambda square minus 6 equal to 0. Group them properly. This is minus lambda cube, this is 5 lambda square and plus lambda square, this is 6 lambda square, this is minus 5 lambda. Okay, maybe I have done some mistake here. When minus lambda was multiplied to all this, the last one will be a minus 6 lambda here. So hope I have corrected that. Minus 5 lambda minus 6 lambda will give you minus 11 lambda, and then plus 6 has to be 0. Maybe that minus can be taken common, and then this is lambda cube minus 6 lambda square plus 11 lambda minus 6 equal to 0. So what was needed in this problem is the characteristic equation. We got it. Now can you write whatever you got in lambda, can you write that in terms of A? So when you write that in terms of A, you will get the answer. That is A cube minus 6A square plus 11A minus 6I equal to null matrix. So this was very important for us. In the examination they asked, what is 6I then? 6I would be A cube minus 6A square plus 11A. And then what is, multiply A inverse on both sides. So 6A inverse equal to, it is a square minus 6a plus 11i. So this was given as c, the coefficient of I was given as d, and then c plus d was asked in the problem, which is minus 6 plus 11, which is 5. So the whole idea is, can you quickly write the characteristic equation? If you can write it quickly, we will get the answer. So we have one more small section, that is like AM and GM, like algebraic multiplicity of an eigenvalue, the geometric multiplicity of an eigenvalue. Algebraic multiplicity is so simple, students. Suppose if A is 3 cross 3 matrix and it has the eigenvalues, let's say 1, 4, 5, the algebraic multiplicity, so for lambda equal to 1 is 1. How many times this 1 appears as the root here? Only once. What is the algebraic multiplicity for lambda equal to 4? So sometimes I read this as arithmetic mean. So this is actually algebraic multiplicity of an eigenvalue. How many times the eigenvalue is repeating? The eigenvalue 4 is repeating only once. So how many times lambda equal to 5 repeats here? Only once. This is how I find the algebraic multiplicity. Suppose if I give you a 5 cross 5 matrix where the eigenvalues are like this. So what is the algebraic multiplicity for lambda equal to 1? So how many times that lambda equal to 1 repeats here, or how many times does this lambda equal to 1 as lambda equal to 1 appear as a root? It appears 3 times, so the algebraic multiplicity is 3. So how many times does this appear as a root? It appears as a root twice, so the algebraic multiplicity is 2. Suppose you take a I4, which is an identity matrix of order 4. What are its eigenvalues? All the eigenvalues are 1, 1, 1, 1. So how many times this eigenvalue 1 appears in this? It appears 4 times. Therefore, the algebraic multiplicity for lambda equal to 1 is 4. This is a very silly topic actually. Next, let's look at the geometric multiplicity. Students, if you are solving Ax equal to 0, then number of linearly independent solutions, which is called nullity, the number of linearly independent solutions is given by this formula n minus rank of your coefficient matrix. But in the concept of eigenvalues and eigenvectors, we are actually solving A minus lambda I into x equal to 0. In that case, number of linearly independent eigenvectors is given by this formula. It is n minus not rank of A, it is rank of your coefficient matrix. Who is the coefficient matrix here? It is rank of A minus lambda I. This is the common mistake made by the students. So I want you people to correct this. So these things are really important for your exam and you are supposed to revise these things.